person is standing on a merry-go-round. L is the angular momentum vector. It points in the positive z direction, which is off of the surface of the merry-go-round. Let's say the merry-go-round has a mass of 100 kilograms itself, and then the person has a mass of 50 kilograms. And let's say the whole system is rotating with an angular velocity of 4 radians per second, k hat. K hat points in the z direction. The merry-go-round has a radius of 2 meters. Let's find the initial angular momentum of the merry-go-round and the person together as a system. So the merry-go-round can be treated as a disk. Its moment of inertia will be 1/2 mr². The person, on the other hand, should be treated as a point mass because they are revolving around the axis of rotation. So for the person, we should use the formula mr². All right, so for the disk, we're going to have 1/2 100 kilograms and 2 meters squared. For the person, we'll have 50 kilograms times 2 meters squared. Let's see, that's going to be a moment of inertia of 200 kilogram meters squared for the merry-go-round. And we're looking at also 200 kilogram meters squared for the person too. Now the thing that's new in this section is we want to find the angular momentum using the formula L equals I omega. Now, both the merry-go-round and the person are going to have their own angular momentum to contribute to the system. So I'll just write disk here for the merry-go-round. And over here we can put a little subscript person. Okay, so the angular momentum here is going to be 200 kilogram meters squared times 4 radians per second. That's an initial angular momentum of 800, and the units are kilogram meters squared per second. As you can see, the person also has the same moment of inertia. So they're going to have the same initial angular momentum. Now let's add these two together in order to get the total angular momentum. It's going to be 1,600 kilogram meters squared per second. Now, why are we interested in the initial angular momentum of the whole system? Well, it turns out that not only is linear momentum conserved in all interactions in the universe, but angular momentum is a conserved quantity too. So that initial angular momentum quantity is going to be used in the future. Imagine now the person decides to jump off the merry-go-round. Now they need to do this in a way that doesn't impart a torque to the merry-go-round. So they're going to actually step off radially away from the pivot point. In that way, they'll apply a force to the merry-go-round that's directed toward where the thing is attached, and then the ground can exert an equal and opposite force on the disc. But when they push like that, they're going to, by Newton's third law, impart a force to themselves, which takes them off of the merry-go-round. All right, if they do step off, will there be a torque? No. And one other explanation for that is by the formula R cross F, we would see that the R and the F would be anti-parallel, and the angle between them would be 180 degrees. If they did that, then the cross product would be 0, and therefore the torque would be 0. All right, so that's good to know. There won't be any net torque on the system. What do you think should happen to the angular velocity if the person steps off? Will the disk continue to rotate with the same angular speed of 4 radians per second that it had initially, or will that angular speed change? Now, I believe it is intuitive to think that it shouldn't change. So even by Newton's laws, you might think that the object is just going to keep doing what it was doing since no net torque was applied. But calculations will show perhaps a different story. And it has to do with conservation of angular momentum. Let's calculate the final moment of inertia of the rotating system once the person leaves the merry-go-round. All right, so the initial moment of inertia was based on the disk and the person. But if the person leaves the rotation here, then the final moment of inertia will just be based on the disk alone. And we said earlier that that was 200 kilogram meters squared. Whereas earlier, when we had both the entities involved, it was 400. Now let's calculate the final angular speed of the disk when the person jumps off. Now how do we do this? Well, we have to use the idea that angular momentum is conserved. The initial angular momentum has to equal the final angular momentum. Now we can replace L with I times W. On both sides. Now let's plug in the quantities. The moment of inertia before was 400, and the angular speed was 4 radians per second. The moment of inertia after, though, went down to 200. So we can solve and find what the new angular speed should be. It should now be 8 radians per second. Now, one way to test this would be to stand on a merry-go-round, and you can actually move your position in towards center or move out toward the edge and see if the speed of the merry-go-round tends to respond. Another way we can see this principle is when figure skaters tuck their limbs in close In order to achieve a higher speed of rotation, they're using the principle of conservation of angular momentum.